Alright, good afternoon. Let's start with the last quiz. Okay, image normalization and image equalization are same things. No, right? Image equalization, actually, the algorithm is also very different. We have our colors separated from 0 to 55. We're going to divide these colors into buckets of 5. Let's say 0 to 51, 52 to 103 and so on. So let's say fifth bucket of 50. And we're going to make sure that each bucket has equal number of pixels. So whatever algorithm we use for that is called image equalization. There we spread that, and those are very good images for eyes. So they're appealing images, but they are useless images for our deep neural network. Whenever you're equalizing, they're actually bleeding images, which means just to compensate or just to make sure the algorithm works, you're going to send many of the parameters, many of the pixels above 255 also. So it actually oversaturates or over contrasts sometimes images, and that is going to destroy the edges and gradients which we are about to extract. So that is not image normalization. Now, Bayes normalization, as we covered last time, solves internal covariance shift. That is the that is the difference in the amplitudes of the same feature found by the same kernel on the same class, but the class happens to have some different features, or let's say its class happens to have a different color, right? Black cat, grey cat, white cat, same texture extractor, same kernel working for the same class is going to extract the 3 different amplitudes. So we normalize that using Bayes normalization. It reduces the need to get highly hypertuned hyperparameters. Now, as of now, you have not gone into this space of selecting hyperparameters, but once you start training models for state-of-art accuracy or the best accuracies, this is the biggest problem which is going to be. What exactly the weight decay you're going to pick, what is the batch size you're going to pick, what is the learning rate you're going to start with, and there are many parameters you have to pick, and all of those parameter selection becomes easier because of Bayes normalization. When Bayes normalization was not there, you could not have written the way you're writing CIFAR 10 or other algorithms today. Right now, you can just write them and believe that you are going to get good accuracy. But the moment you go for deeper networks and for complicated data set, those parameters become very important. But Bayes normalization has sort of eased selection of these parameters. It helps train deeper networks. We have seen that also. Now our channels are not going to explode to 2000 and 4000 numbers. They're going to be kept in the range. It helps train network faster. Now, when we say faster, we are not saying that one epoch is going to be faster. One epoch is still going to be longer. Bayes normalization takes some computation. So each epoch is going to be longer, but instead of taking 40 epochs, I'll take, let's say, 20 epochs. So we are going to save some time overall. Just like a highway, but you have to pay for that. A layer has 32 channels. For Bayes normalization, it will have 32 means and 32 variances. Right? So for each channel, it will have a separate mean and a variance and a mu and a gamma and a beta. So there are 4 parameters for every single channel we are going to create. So if we have 32 channels in a particular layer, there we are going to have 32 means and 32 variances. If we use regularization, we can solve overfitting. We discussed this problem last session as well. Kernel values are going to be close to 0 or small, right? It's guaranteed to get higher validation accuracy, not true. It is guaranteed to get higher training accuracy, that is also not true. Quite clear? Okay. Now, if you create a data set in such a way that the images are automatically normalized, then would we need Bayes normalization? Yes, we'll still need Bayes normalization. When you're using image normalization, you're essentially doing Bayes normalization for the first layer. But after that, we still need to have normalization done by Bayes normalization, because that effect is going to be just consumed by the first layer. We still have to have second, third layer normalized, so our kernel values can actually be in control. Now, Atros or direct kernels can be used for image segmentation. These are some of the use cases we saw. We have super resolution related problems. We have denoising. We have key point detection, which is going to be human pose estimation, or face landmarks, which is better for capturing global context compared to normal convolution. Your Atros convolution is going to be much better. Okay, now consider a layer of resolution of 64, 64, 128. In the next layer, we intend to add normal 128 kernels of size 3 x 3. Assume this adds X number of parameters. If you're going to use stepwise separable convolution, how many parameters we are going to add? Now, let's write that a normal kernel will need for this operation. We are going to need a 3 x 3 x 128 x 256. But if you use stepwise separable convolution, our first step is going to be using a 3 x 3 x 1 for 128 channels. After this, we are going to concatenate all of these channels, and then we are going to perform a 1 x 1. So we are going to use a 1 x 1 x 128 x 256. So 128 and 128 and 128 are gone. This is 256 into 9 divided by 256 plus 9. That is 256 into 9 divided by 256 plus 9, 265. Right? This divided by this is some number which is close to 1, and this divided by this number which is slightly bigger than 1 is going to be this one. It's cool. Okay, select which all are true. Good convolution should help in handling scenarios where object size might be different. That is actually a topic of the session today. I'm going to share with you how group convolution help us handle different size objects and different size receptive fields. Dilated kernels are beneficial when dense resolution channels are expected. Right? Dense resolution channels are when the output is not just 10 class but a big channel, 400 cross 400 cross 10. And dilated kernels are going to help us that we can increase our receptive field fast. We can increase the receptive field fast, so we don't have to add as many layers. Spatially separated convolutions are preferred early in the network. Now, this we did not cover. This is a normal kernel, which is a 3 cross 3 cross 3, convolving on 3 channels which are coming in. If we use depth-wise separable convolution, then we are going to use 3 such 3 cross 1 cross 3s, 3 cross 3 cross 1s, right? Right, this is normal, this is depth-wise separable. Now, if we use spatially separable, we are actually going to use a 3 cross 1 cross 3. These are spatially separable convolutions, and the way we are going to use them is, let's say we have a 56 cross 128. We are going to use 3 cross 1 cross 128 cross, let's say 128. Right? This is going to result in 56 cross 54 cross 128. This will be followed by 1 cross 3 cross 128 cross, let's say a bigger number, 256. And that is going to give us 54 cross 54 cross 256. Right? So essentially what we are trying to say here is that if I want to get a normal 3 cross 3 kernel, I can use a 3 cross 1 kernel followed by a 1 cross 3. Right? So sort of equivalence is what we are trying to measure here, or lay the foundation for. We are saying a 3 cross 3 is sort of equal to 3 cross 1 followed by 1 cross 3. Right? But if you think about this, 3 cross 1 will be able to do, let's say, extract features only in one axis, and 1 cross 3 will be able to extract features only in the other axis. So the features are similar, or the features are simple, then I can use possibly these two different dimensions to create those complicated features, those simpler features. But the features are complicated, where we need an interaction between x and y, for example x square plus y square, or x into y, like a parabola, then I cannot use any of such filters. So generally what you're going to see is that whenever you use spatially separable convolution, we use them early in the network, where the features are still very easy to create. The deeper you go, you cannot use these properly. And in fact, these days, spatially separable convolutions are not used at all. We in fact rather use depth-wise separable convolutions or normal convolutions. Okay. This is something good to know, because you may want to experiment with them, but you need to realize that they will not be able to give you the kind of accuracy or performance your other depth-wise separable or normal convolution can. Okay. Assume two layers are merged together. One should prefer merging layers like this, where we make a 32 plus 32 equal to 32. We are adding here, or we actually concatenate them by placing them on the z-axis and then use a 1 cross 1 kernel. We are saying that these are 32 channels coming from the layer 1, and these are 32 channels coming from the layer 2. We want to merge them. Now, let's say this is 5 cross 5 cross 32, and this is also 5 cross 5 cross 32. If this is true, then I can actually add them element wise. I can then create a 5 cross 5 cross 32. This is one option. Another option I have is that I actually concatenate them. I keep them on top of each other, and then use a 1 cross 64 cross 32, and then I get 5 cross 5 cross 32. Right? Now, this is a preferred method. This is a preferred method. So this will give you higher accuracy, but there's a cost involved. Good. So assume that two layers are pretty much, one should prefer adding them as compared to concatenating them and followed by 1 cross 1. That is why this is false. But state-of-art networks merge them. Like ResNet, they are going to add them. Inception, however, is going to stack them. Inception is going for the concatenation part. In resident, we are going to be adding them. So when we cover resident, I'm going to explain why resident decided to actually add, even though it is going to reduce the overall accuracy. Now, dilated kernel should be better for scene classification networks as compared to object detection networks. That's true. When we actually need to classify scenes, we need to have much bigger idea, right? Edges, gradients, textures, patterns, parts of objects, and then scene. Which means my kernel needs to know that this chair and this table, because of that spoon, makes it a dining table. Because of that pen, makes it a study table. Because of that hammer, makes it a judge table, and so on. So based on some additional information, your scene actually becomes very different. The context is required to classify a scene. Any question on the quiz?
In the same question, the group convolution. So we are saying it's a 56 cross 56 image with a big cat and a small cat in it. This is what the object size difference is.
No. We're saying group convolution should help in handling scenarios where object sizes might be different. We're saying that I have an image data set of size 56 cross 56, but in one my dog looks like this, and in other my dog looks like this. Right? So object sizes are different. Alright, let's start with today's session then. Now, today we are going to cover modern DNN architectures and image augmentation. I'm going to take you through some of the architecture which are important. I have a bias. I have, let's say, I love some of the architectures, and you might decide that you might love some of the architecture. So generally, there's a fight like Canon versus Nikon. If you have bought a Nikon is the best camera for you. If you bought Canon after spending 4 lakh, Canon is the world's best camera for you. So it is split like that. It's not like Android and iOS as of now. It's not like Samsung and iOS, where we have a clear differentiator. And even if you say that Android is better, but somewhere down the line you know that's true. But still, iOS is iOS. Right? It's like your best friend asking you that you have 2 girlfriends and both are asking you, do you love me? You love one more than the other. You know internally. But to the other one, you're still going to say, yes, I love you. But internally you're thinking, but. Right? So whenever you have that but, there's a clear differentiator. In Canon and Nikon, people don't have that but. People who are real photographers, they are split between these 2 guys, right? And these 2 guys for us is going to be resonant and inception. I have a bias towards resonant, so I'll be upfront, and I'm going to share my perspective of what inception, what resonant is. Okay, now this is a competition which literally has defined the image processing or computer vision revolution for the deep neural network. This is called ILSRVC, which is ImageNet competition. Here we have a data set of around 1000 classes, around 1.2 million images, and we have to classify this as a dog, cat, a candle, and so on. Now, the first 2 years, the competition was not won by deep neural networks. Imagine you decide to start an electric car racing, but for the first 2 years, petrol and diesel car won, because you forgot to mention that those cars are not allowed. So first 2 years, actually your electric cars did not win. These are not deep neural networks, these are traditional computer vision approaches. Then AlexNet in 2012. Now, you'll not believe AlexNet did not invent anything which something which we are using today. False, but I'm going to correct myself. Now, AlexNet is not known for its architecture. It is not known for batch normalization, that was invented in 2015, 14 and 15. It is not known for dropout or image augmentation strategy. It is not even known for backpropagation. All of that was invented in 1989 as well. AlexNet is known to have solved one very critical problem. ImageNet database was huge. We were not able to process the data. He was able to figure out how can I actually have 2 different GPUs solve the same problem. Is the part clear? The contribution was because one GPU was not capable of handling the whole data set. He was able to write an algorithm where the backpropagation can happen on 2 GPUs, which is something we use today. But the contribution is not on the architecture, or suddenly he solved something so the DNN actually started giving us much better performance. Is the part clear? Till that point, we had no idea how do we actually train the network on 2 GPUs, and he was able to fix that particular part. And the moment he did that, you see the jump which is there in the accuracy. These are top 5, by the way. These are not top 1 accuracy. Top 5 would mean that out of 1000 classes, image goes into the network is going to say 5 names. It may be a dog or a cat or a lion or a plastic ball or a basketball. So that is top 5. We show top 5 because it looks cool. In top 5 we can say that accuracy is 2.99%. That's the error basically. Error is only 2.99. Top 1 was not shareable. Right? Sometimes people ask you, maths mein kitna aaya? as a kid, you are going to tell them overall I scored 80. You're not interested to share your marks for a specific subject, you are caring, so that is what is happening right now. But things have improved. Our top 1 accuracy is at 87% now, which is not bad. So we can actually show a graph for top 1 also, but for quite some time we are actually using a top 5 graph. Now, you can also see that over a period of time, the number of layers are increasing. We have 8 here, 19, 22, 152, 200, and now we are actually going beyond. We have 1000 layer networks as well. So first of all, this is VGG and this is Inception V1. Both came at the same time. Inception won the race. It had 22 layers, and VGG had 19 layers. I've shown you the VGG architecture. It's a simple sequential architecture. But Inception is not a sequential architecture. It's a parallel architecture. We are using many different kernels in Inception. And this is where we invented batch normalization, and after that it's just explosion. We just keep on increasing, adding layers. Is the part clear? Now, this is a sequential architecture where we stack layers on top of each other. This is layer 1, layer 2, forward max, pulling, then other layers. And
on the row. So when we talk about 8 layers, 9 layers, is it not possible to have 22 layers which AlexNet is defined with 8 layers?
It is not possible to have 22 layers in AlexNet? No. Because batch normalization is not there. And that architecture will simplify it. The simplest possible architecture with largest number of layers without batch normalization you can create is VGG. So this VGG architecture gave that performance without batch normalization. And of course, that is why today we prefer VGG. It's a simple architecture, added batch normalization improves even further. But it can never compete with the parallel architecture.
The accuracy improvement is just a result of increasing the number of layers?
That's what I'm going to cover. Is the part clear? Alright. Now, this is sequential architecture. And we are looking at different layers, edges, gradients, textures, patterns, parts of objects being extracted right now. But these are parallel architectures. This is Inception V1. This is the 2014 Google Net. This 6.7% error network is this guy. Right? Now, if I zoom in, what you're going to see is that this is the end of this is the output of the last layer. It goes inside many different kind of layers. Many different convolutions are happening right now. We concatenate them, and then we proceed for the next layer, right? Same architecture is followed in different blocks. You're going to see in deep what these blocks are, but the problem now is that there are too many layers, right? If you actually count, you'll see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and the way they have counted, we should come at 22 layers. So essentially looking at 22 layers here. Part clear? Now, without batch normalization, that should not be possible. You cannot create a network with 22 layers without batch normalization, and batch normalization is not invented. But they wanted to go deeper. The field since early on has been the deeper you go, the better the network is. People somehow know that, and we are going to discuss if that's true or false. But that is what they're trying to follow. But if I don't have batch normalization, I can't go deep, and the reason I can't go deep is because my gradients fail. The gradient will start from the last layer, it will die down somewhere in between. It will not be able to go back. We see gradient vanishing problem there. So what these guys smartly did is, this is a loss function, gradients are flowing back, they're dying and they have died. I add one more loss function. Now I can flow my gradients from this side. Now they enter the network, let's say they're diminishing and died, but I have yet one more loss function. And from this loss function, I can pump in more, so these guys can actually reach the back. Right? It's like you're trying to make a bridge. You floated a tender, 200 crore. Before the bridge work started, 100 crore taken by politician, 50 crore taken by other guys, 50 crores left. You know you can't make it 50 crore, you pump 200 crore more. Now half the money go to contractor, 100 crores again gone, you're again left with 100 crore, you pump in 200 crore more, 100 crores again gone, but finally you are left with 200 crore. And that can make a bridge. So overall cost is going to be 600 crore. That is what is happening here. We have 3 loss functions. Now this is the only network which is created with 3 loss functions, and these loss functions are not used for prediction. They are only used for training. They're just trying to make sure that I can pump in some of the gradients back. It's not that if an image comes out from here, I'll use this prediction in the final network. The final network still depends on this guy. Once the weights are trained, we don't need to care about these 2 loss functions. And they're also called auxiliary loss functions. They're just there for the training part. The part clear? So if batch normalization wasn't invented and we want to go to 100 layers, we'll have to punch in different routes for the gradients to flow. Now, after this, we invented batch normalization, so it was possible for us to go deeper without doing such a thing. And that is when ResNet came in. What you're seeing on the left side is our VGG, and in VGG we have 19 layers. We are adding these layers. If we now just stack more layers in a VGG and call it a 34 layer VGG, it's going to look like this, but it's not trainable. The reason it's not trainable because the weights are going to die. And we have to again do that puncturing thing. If I get punctured somehow, my loss function is in the midway, then I can actually back propagate properly. That is what ResNet guy is doing. If you think about it, these are skip connections. I'm going to explain what skip connections are, but you can right now imagine them being a highway of the forward and backward information flow. Let's look at the backward information flow. If I'm calculating my gradient here, I can talk to this layer, but I can also go in this direction and talk to this layer directly. I can also go in this layer and talk to this layer directly. In fact, I can avoid every layer and follow these skip connections and talk to my 7x7 layer also. Right? This is what is happening in ResNet. We are going to go look deeper inside. Part clear? Okay. But why? How does going deeper is helping? Right? Now, you've heard that the deeper you go, the better the network is. If that is true, we would be stacking VGG-like networks. Batch normalization is invented. I will just stack more layers. I will add 100 layers like VGG, right? Just simple normal convolution in sequence and sequential architecture, and add batch normalization. It should work. That doesn't work. What works is parallel architecture going deeper. So there's a need of parallel architecture. There's not a need of sequential architecture is going deep. We are actually trying to make sure that parallel architectures can go deeper, and that is where the magic of receptive field comes in again. Now we know that we take our image and we are trying to divide our image into edges and gradients and textures and patterns and parts of objects, right? Now let us imagine that our image receptive field for 400x400 network, if our image, and this is what I've told you since beginning, the size of the object is equal to the size of the image for the concepts we are learning. So what we are discussing is true for this fixed size network. If your data set is 400x400 and then you take a VGG and then you make VGG go deeper, it is going to work for you. But that is not how our data set is. In our data set, we have object size 50, 100, 200, 251 and different variations. And that is why VGG will not be able to do such a thing. Now, you remember that we discussed the size of the object need to be equal to the size of the image for the concepts we are discussing, right? Now we are going to break this particular concept. What we are asking now is, what if the size of the object is not equal to the size of the object, which is nearly always the case? What if the size of the object is not equal to the size of the image? If you are reading object there, you are already sleeping. Right? What is this word? Image. Which is always nearly the case. Right? Our object size is not going to be equal to the size of the image. Now let's see what actually happens if the object size is not equal to the size of the image. This is input image coming at 400x400. Let us assume that we have extracted our edges by this time. You are seeing receptive field increasing as I am drawing lines. These are my edges and gradients. This is my textures, this is my patterns, and this is my part of objects and predictions as well. Let's say we have 4 blocks which we are looking at, right? And this is 400x400. Just for calculation base, I'm going to say this is 100, 150, 200, 250. 400, 200, and 100. So 100, 200, 300, 400. Just for calculation, keeping the calculation simple. Is the part clear? Basically some numbers, but for calculation's sake, let's say these numbers are like that. Now, if the object size happens to be 200, by the time I am hitting my receptive field of 200, I've seen the whole object, right? And if you remember, 1 pixel becomes 3 pixel, becomes 5 pixel, becomes 7, 9 and 200. So whatever object you're looking at is now represented by 1 pixel. That is this pixel which is representing it. Now the task of the kernel which you are now adding on top of that is to transfer that information, because you've already identified the object. You've done whatever extraction of features, kernels and parts of objects was required is already done. Now what is required is to pass on this information to the last layer. C-cross-trees are not known for that. C-cross-trees are known to extract features. They're designed to look at the features and convert them into something different. Right? We are never going to have a 3x3 where all the kernels are just 1x1. All the variables are just 1x1 values in the 3x3. Then I can potentially transfer that, but you're never going to get such a kernel. So what happens? we start detecting this object, but the context of the vector, context of this object gets lost and lost and lost, and finally we have a faint idea of that object being present. VGG sucks at small size objects. It is not a good network to identify small objects. And if you want a proof, you can look at YOLO V2. YOLO V2 uses VGG as the backbone. They trained the whole YOLO network and then realized they're not able to identify small objects. What they had to do? Skip connection. They had to go to 13th layer where the receptive field was equal to the size of the objects they were missing. They connected that to the last layer. Now that layer can directly talk. If you have found a dog here, directly the skip connection is going to pass on the information to your last layer. Is that clear? So you're doing the skip connection part here. And this is the problem with the sequential architecture. And this is 200, right? Now if I don't look at 200, if I look at in fact object of size 100, so I'm going to draw 200 again. 200, this is my image object size, and it becomes 100, edges and gradients, textures, patterns, part of objects and objects done. If I go for 100 now, I'll be done here. 50, in fact, even difficult to draw. Is it quite clear? This is what happens when the size of the object is not equal to the size of the image, which is nearly always the case. Sequential architecture is very beautiful for making sure I can identify these objects, but in case the object size is smaller, it struggles to carry that information forward. Is that clear? Okay.
We do batch normalization. We normalize all in terms of training. We do the same VGG doesn't have the batch normalization.
Even you have batch normalization is trying to make sure that black cat, white cat, and grey cat have a similar output. Not the small black cat and the big black cat. So we are not normalizing for the size, we are normalizing for the colors. We are normalizing for the amplitude of the features found.
And size is not a feature.
Size is not a feature, as in? There is no kernel identifying size.
Okay.
In ResNet architecture, skip connections are skipping every two convolutions, and they are connected. And you said that the backdrop values can flow towards the top also. But does it actually flow towards the top? Or
I'm going to cover. No, I'm going to cover that. We are going to cover ResNet and reception board today. So give me some time. Now parallelism helps take care of requirements of different receptive field requirements, right? And we're going to see this in a very short while. What we're trying to say here is, if my network is not sequential, but our network is parallel. First of all, what is a parallel network? This is a sequential network where one layer gains the output of the last layer and convolves and passes on the output to the next layer. Sequential, this is sequential. Parallel architecture would be that, let's say we start with one layer, we convolve separately on this layer, let's say by a kernel of size k1 and another kernel size of k2. And then we concatenate them or add them. We will decide what we are going to do, but we merge them somehow and we create this new output. Is clear? Now, our K1 can be 3 cross 3, our K2 can be a 5 cross 5, our K2 can be a 1 cross 1, our K2 may not exist also. If our K2 does not exist, it's going to look like this. This convolution is happening, and we can call this convolution the identity mapping. What is the identity kernel? It looks at exactly the input, it creates an input and creates the exact output. That is the identity kernel. So those are the kernels I'm using. This kernel can be 5 cross 5, 10 cross 10 or not even there. But this is group convolution. Not in a stricter sense, the definition of group convolution is slightly different, but this is one of the group convolution which is possible. But clear? Okay.
So here we have reached the edges.
Here?
In the same. Here we have reached one layer, or
this is called one layer.
this is one layer.
This is called one layer. So input, output, whatever in between is one layer.
Is it a good way to understand that when you want to create a number of channels like 48 from an input of no channel, you want to create a number of feature maps and number of
sort of.
But when you want to group them with 1 cross 1 convolution, when you want to finally convolve or finally merge them, if the sizes are different, how are you going to?
I'm going to explain. We use padding there. Now, parallelism helps take care of requirement of different receptive field required for different objects. Let's first understand this point. what we want from architecture is that my receptive field should be 400 here, my receptive field should be 200 here also, my receptive field should be 100 also. We're trying to make a network where the receptive field on a network is not constant, because the size of the object is not constant, which means even if the size of the object is 50, that receptive field is available at the end. Somehow I can take that feature and directly connect to the last layer. And the way I can do that is by connecting this guy to this guy. I can connect this guy to this guy, or I can basically hack in that line, or I can do this direct connection also. If I do that, then this last layer will have information about all the receptive fields, and now it can process properly. We're going to see how we do this connection, but this is the idea we're trying to use. Is it quite clear? And when you do this, you are actually going to be using less number of kernels. You will need less kernels. I'm going to explain that part also, that when you actually do parallel, you will require lesser number of kernels as compared to a sequential architecture. Okay, now let's look at first of all, what is the receptive field on network? What if the receptive field on network is much more than that of the data it is trained on? Right? Let me first finish this part and then I'm going to come back. I'm drawing an inception module right now. Not an exact inception module, but it looks exactly what we are. It's very similar to what we are drawing right now. Let us assume this is the image which is coming in. What is the receptive field of this image? 1. Right? I'm going to convolve this by a 1 cross 1. I'm not interested in writing channels right now, but imagine they being same and we are going to concatenate and we can handle them. I'm also going to convolve this by a 3 cross 3. If I convolve on, let's say 28 cross 28 by 3 cross 3, the output is going to be 26 cross 26. But we are going to use padding to make sure that the output is same, because we have to concatenate or add them. I'm also going to convolve this by a 5 cross 5. If I convolve this by 5 cross 5, my image size is going to be even smaller, so I have to pad even more. But I'm going to make sure the output is always 28 28, because that is what is coming out from the 1 cross 1. Now I'm going to either add them or concatenate them. We are not discussing that part right now. In case of inception, we concatenate them. In case of resident, we add them, right? But that is not what we are discussing right now. We are discussing what happens to the receptive field. Now, what is the receptive field of the input image? 1. What is the receptive field through this route? 1. Has not changed. What is the receptive field through this route? 3. Has changed. What is the receptive field through this route? 5. So what is the receptive field I am carrying right now? 1, 3 and 5. Cool. Now magic happens now if we add one more layer on top, right? If we add yet one more layer, and this layer again happens to be 1, and let us say 3, and now 5, and we are again going to look at that, concatenate them. Alright, now this route is not going to change the receptive field. It's going to keep it as it is. This is going to be 1 and 3 and 5. This route is going to add a receptive field increase of 2 to everyone. So this is going to be 3 and 5 and 7. And in this route is going to add a receptive field increase of 4 to everyone, and that is going to become 5 and 7 and 9. That means I can actually combine this just for writing purpose. I can say I get now a 1, 3, 5 and 7 and 9. Right? Now if I keep on doing this, let's do this from scratch. My receptive field of 1 after the inception modules becomes 1, 3 and 5. After another inception module it becomes 1, 3, 5, 7 and 9. After another module it becomes 1, 3, 5, 7, 9, 11 and 13. Right? If I add yet one more, it's going to become 1 and 17. So if I keep on doing this, and remember we have max polling, we have stridef2, we can use something to immediately bloat this up, right? We don't have to continuously do this. Same practice and same structure is going to follow. But finally, if I'm stopping at, let's say, receptive field of 224, I'll actually have 1, 3, 5, 7, 9 and all the receptive fields which are required till 223, 224, 225. Let's write 224. It could be 223, 224. Let's not fight on that, but just get the emotional part here, that we will get all the receptive fields. In between we would have used 1 cross 1 somewhere, right? And we are doing concatenation part also. So in concatenation all the receptive fields are flowing through, and we would have done 1 cross 1 somewhere also. What is the task of 1 cross 1? combined channels, and you are carrying a receptive field of 25, there is no object of size 25. What is the point of carrying that forward? 1 cross 1 is going to merge it and make it disappear. Is it clear? So finally, sorry?
What is the last part?
Let's say we have 1, 3, 5, 7, 9 and all the receptive fields, right? Whenever you're going to use 1 cross 1, it gets to decide which channel to multiply with what amplitude. Our receptive field 25 is not required. I'm going to multiply with 0. So whichever receptive is not required, a 1 cross 1 is just going to rip it off. It will not be carried forward. This is the inception for you. Okay, now let's look at ResNet. In case of ResNet, this is the input image which is coming in. The receptive field of input is 1. It is going to be convolved by 2 layers of 3 cross 3. What is the receptive field now? 5. I'm also going to take the input and I'm going to add this input here. So this guy has a receptive field of 1 and 5 now. Now if you follow the same stuff that we did on inception, this input image is 1. If you add a resonant block, it becomes 1, 5. If we add one more block, let's see what happens if you add one more block. It's going to add a receptive field increase of 4 to these guys. So these guys are going to become 5 and 9, but I'm going to be adding 1 and 5 as well. So I have 1, 5 and 9. So if I want to continue this table, I'll have 1, 5 and 9. You add one more, it becomes 1, 5, 9 and 13. You add one more, 1, 5, 9, 13 and 17. Same thing is going to happen. Now if I continuously add them, I have a stride of 2, I have the max pooling layer between my network. It's going to double the receptive fields and allow us to move forward, double the jump parameter basically. So finally when you stop, you may have a receptive field of 1, 3, 5, 7, 9 and all till 223 or 225 or wherever you're stopping, or 255. Is that clear? And same logic follows here also. 1 cross 1, that is why 1 cross 1 is required in a network. It's not that we are using 1 cross 1 only because it allows us to do something like a parameter reduction or mixing some of the channels. We actually need it. If you don't use it, you will carry forward information which is not required. Right? When you go on travel, you don't carry the boxes of the products you bought. You're flying to, let's say, London or New York and you want to carry a laptop, you will not carry the laptop box in which the laptop came in. You're going to throw away all of that stuff. You're only going to carry a sleek MacBook. Instead of MacBook plus a thermocol plus the box plus the wrapper around that. That is what 1 cross 1 is going to do for us. Throw away the context which is not required for us. Is the part clear? Okay. Now if that is clear, try and answer this question. Read what if the receptive field of a network is much more than the size of the image? We have been discussing, now we discuss the other part, right? My object size is equal to image size, let's say 400 cross 400. But we know our object size are smaller. It may be 400, maybe 300, maybe 250. So we need a parallel architecture to handle that particular part. We discussed that particular part. But what if the receptive field, we keep on adding layers? We have discussed, right? Going deeper is doing something. Going deeper is increasing receptive field. So now when we go deeper, my receptive field of the network is going to be more. If I cross the receptive field of the image size of, let's say, 224, I'm at 400 right now. What is happening?
You discard all the layers above 224. Receptive fields.
Please remember, it's a sequential architecture which we are not discussing, right? Sequential architecture answer is different. Parallel architecture answer is different.
We will start losing information.
Then why are people going deeper? Okay, I'm showing you some of the channels which have receptive field is taken from a network where the receptive field is much more than the size of the image. Right? Now here, what you're seeing is a receptive field of a network which is much bigger than the size of the image. What you end up doing is, okay, first of all, I want your imagination to work with me right now. Okay, I'm going to draw a receptive field. This is a 3x3 kernel with the receptive field of 3x3 is convolving on top of this image. Can you imagine this moving from this guy to this line and then again and then again? You can imagine this happening right now, right? Okay. Now I'm going to increase my receptive field. My receptive field right now is of 19 cross 19 on an image of, let us say, 64 cross 64, right? I'm convolving right now. So this receptive field is searching for object on top of this image, right? You have this as your object and this block as a receptive field. It is moving on top of your image and trying to find out, have I found my object or not. Got clear? Okay, that's the size of the image and that's the receptive field which is trying to convolve on top. We are right now moving like this, right? Okay. This is 64 and let us say this is 16 right now. Let us go to 64 and the receptive field also 64. If the receptive field is 64, then you can't convolve. You're just on top, you're going to multiply everything and you're going to be done. But if now receptive field is 200 and the image size is 600 or 64, what is going to happen is, this is your image, this is your receptive field. You are going to move your receptive field on top of your image, right? And I can actually add many templates inside the receptive field for them to match. I don't have to create one object inside my receptive field. I can create many different orientations of birds. Now when I convolve this huge template of birds in different directions and different orientations on my channel, one of them is going to fire. It is going to find a bird looking up, down at a slight different angle, right? I cannot have a single kernel which can define that kind of scene. It cannot define, there is no one kernel which can say that all the bridges are going to have black structure followed by that kind of cloud, followed by that kind of sea below it. So I have to create this interesting mesh up of different patterns which can be put together. And now when I convolve the receptive field on my image, I will find it. I will find that kind of pattern, right? This is one of my favorite examples. First of all, let's cover this one. Now you are going to capture a photograph of a dog. Which dog, which orientation, what size? Now that can be handled here. And now because I am talking about a parallel architecture, I can put in a smaller dog also, which is shown here. If you think like humans, and we will think like humans, and let's say we have to figure out a particular circle. We have to identify a circle in a network, right? You will think like a circle. You think your kernel is going to be trying to identify a circle. Look what the network has done. Circle, which radius? What if it's slightly oval? Yes, your network has figured out a spiral for that. Network has figured out if I actually use a spiral and use that spiral to find a circle, I can find out any kind of radius for any circle. I can also figure out what ellipse you are looking at, right? Not only that, there are many different search structures inside it. So I can now handle many different sizes of the same objects also. So when your receptive field actually increases, when your receptive field goes beyond the size of the image or the objects you are seeing at, you are actually going to make different patterns. Imagine that this Iron Man, we have this pose and the other pose and the other pose and all structured together. One of the poses is going to meet or match this particular guy. Right? See, receptive field is a notional concept. There's nothing linked with the receptive field. The output is still going to be those 10 numbers. Size of what?
Size of output.
Size of output is 10.
When you convolve the input is 10 and the receptive is, let's say, 20 or something, and the output is going to be 10.
We only convolve by 3 cross 3. The kernel has a receptive field of 400 cross 400. Right? So that is something you have to like believe and observe of what is happening here. Our kernel is just 3 cross 3. It is still looking at 9 pixels. But the receptive field overall it has is 400. If you can understand in the normal network, now you are saying that your kernel, the same 3 cross 3 in the last layer, has a receptive field of 800, which means when it is convolving, the overall set of parameters it has all the textures, all the different kind of patterns for the same object inside. Now just look at more examples before we build this intuition.
So the receptive field is built by lot of kernels.
Receptive field is built by a lot of kernels, correct. So the first you're seeing right now, the first output of the receptive field you're seeing right now is actually trying to capture human body parts. So which part, in what orientation, something which is very difficult to handle. In fact, this is the gem. What you're seeing right now is a fruit stall. So is it going to be oranges followed by mango followed by banana, or it's going to be mango followed by banana followed by oranges, or it's going to be oranges followed by kiwi followed? You have different patterns you have to find there, right? No one pattern is going to work for you. But if you can create something like that, and if this convolves on top of that area, many of these guys are going to fire. And all we are interested in is that output of this channel must be high. If I keep oranges and apples and other things in one channel, and that channel convolves on my fruit stalls, some part of the channels are going to be activating. So the output you're going to be getting is going to be pretty high as compared to one single pattern which you're trying to find out for one single dog or one single fruit stall. Right? Look at this guy. Here you're trying to figure out architectural arches. Something you've seen in Rajasthan and similar area, right? Now, which arch? How long should it be? How many windows are going to be inside? We can't figure that out. So our network actually has decided to make a very simple, a beautiful structure which can actually look inside and find it out. Look at these two guys. You're trying to find a flower where exactly the leaves are going to fall. Which orientation is it going to fall? When you convolve on top, you should be able to find the leaf and the flower also, right? Leaf kernel has done this work. Leaf kernel is going to give you the leaf. The flower kernel has done this work. It's going to give you the flower output. Now, what size of the flower are you going to get? And which orientation leaf is going to fall? This image right now is the car dashboard. Which car's dashboard? Hyundai or let's say Maruti and so on. And again, the buttons are going to be placed in different order. So when you increase the receptive field, you actually are trying to make a bigger template. It's a bigger sketch which is going to convolve on a smaller image, right? Your sketch is going to be much bigger. This is going to now convolve on top of image. So you can imagine that very small 3x3 which is convolving on top, trying to identify that. But internally it has a receptive field which is much higher. So internally the receptive field is something like this. This is what it's trying to find out. The receptive field, as you know, we are talking about global receptive field. It is combination of 3x3 plus the last 3x3 plus the last 3x3. So when you're talking about a bigger receptive field, you have to tell yourself it is a combination of the complete view seen by the 3x3 you are interested in and all the 3x3 going to the image. It is not one 3x3 which has this receptive field. That is accumulation of all the work done by all the 3x3s linked in a particular network.
So it has become like a master superset right now.
Yes. So right now you're looking for a superset using which you can find. Now another simple example. My image size is equal to the object size is equal to the receptive field. I will be able to add my A detector there. But is that the only A which is going to come? You may use Helvetica, you may use sans serif, many different kind of fonts, right? You may use Gotham, you may use Arial, Roboto. There are many different fonts which are going to come, and my network is not going to be as accurate now. It will activate on top of those alphabets also, but the activation is not going to be really high. But if you allow me to go for a higher receptive field, I can actually do something like this.
Earlier, for each of this to detect,
you would need a separate kernel. Earlier, if you were trying to do something like that, you would need a separate kernel. And that is why when you go parallel, you will need actually less number of kernels as compared to one single monolithic architecture where you're trying to identify this and this and this and this and this. If these 5 are there, we discussed that, right? The number of kernels directly linked to the complexity or the intra-class differences. This is intra-class difference. You have these kind of A's, so you have to increase the number of kernels now. But now because the receptive field is large, all the kernels which are trying to extract these edges and gradients can combine and make some complicated patterns and throw on this receptive field. So you will have one single big huge receptive field kernel where all these patterns are going to be there. Now when this guy convolves, it is going to find one of the A which I have. And please remember, this is a deep neural network we are talking about. It will not have a Helvetica font, it will not have an Arial font, it will not have a Roboto font. It will have some beautiful mix, some optimized version of A which will work for all, like you saw in the circle. right? The maximum way we can think is that I am going to find this circle, so I need a kernel of which can identify this circle and maybe this circle. Maybe you run a k-means clustering on your dataset, figure out that the circles you need is 3, 5, and 7 in size, and you're going to make a kernel of that size. What DNN is going to do? No, I don't need that. I'm just going to make a spiral. Now I don't need to worry about what is the size of the circle I'm interested in. So DNN can do this. We can't think like that. DNN can optimize one particular channel, which can actually look at many different kind of inputs coming in. You see, what is the middle channel right now? What do you think is it? It's a dog nose extractor. Right? So different orientations and different sizes. What is the last kernel? It's a dog with a big ear. Right? Where is the ear going to fall? Is it going to be on the left side, right side? Is it up and down? So all that can be beautifully made by this beautiful kernel.
How you are getting this image?
How we are getting this image? We go to a particular kernel. So the way I like to explain this is that imagine that we are again in the first session, and you are an E extractor. Right? If I show you this particular page, all you're going to do is to give me all the E's. So in the URL, you're going to give me the E. In the edges, you're going to extract both the E's and give it to me. That's your task. In algorithm, what we're going to do, we're going to ask you a very simple question. What is your dream image? Then you're going to go mad. If I ask you what is your dream image, you're going to imagine that you're just in the space of E's and E's. There are beautiful E's all across. One big E, small E, that E combined with smaller E, which is hanging below that. That is exactly what we're doing. We're asking a particular kernel, what channel should I create so you get the highest activation possible?
Actually, how are you showing us this image, but actual kernel size is 3 cross 3?
Kernel size is 3 cross 3. That 3 cross 3 is going to talk to 3 cross 3 before that. That 3 cross 3 is going to talk to 3 cross 3 before that. And final 3 cross 3 is looking at the image. You're asking the 19 3 cross 3, what image should I create so your value is highest? So that 19 guy is going to tell 18 guy, dude, this is what I need. 18 is going to tell 17 guy, this is what I need. Communication happens, and finally we are going to tell the first layer, that is exactly what we need because boss needs it. Boss wants to feel high. If boss wants to feel high, this is the image we have to create. So we create these images pixel by pixel. There are many forward pop and backward pop happens to create this kind of image. But what we are seeing right now is the dream image. It's a dream world of that particular kernel. Right, imagine that you like chocolates so much. What is the dream world for you? Your chair is chocolate, your watch is chocolate, your walls is chocolate, it is raining chocolates. That is actually what is happening right now for these guys, but in a mathematical way. And the boring mathematical term for that is what is the highest activation which you can provide to me, and what is the image I should give you for that high activation. So communication triples down for layer 19, 18, 17, and finally at the first layer. With the first layer we tell that that's the high value we want. A simple way to imagine this kind of algorithm would be, imagine that after a multiplication of 2 3 cross 3 areas, 1 3 cross 3 is my kernel, and I have some specific values in my kernel. First of all, we are talking about a complicated kernel right now. We are talking about a 3 cross 3 cross 512. Right? That's the kernel we are talking about, and we want to look at the visualization of this guy. Right? If I want to look at the visualization of this guy, and we are talking about the highly activated channel, I'm going to take the channel number 1. I'm going to ask that channel number 1, what is the channel should I show you so you give me the highest value possible. That's a maximization problem, and that is going to say that okay, I need this particular 3 cross 3. This is how it should look, so I convolve on top and give you the high value. Then I'm going to look channel number 2. I'm going to ask that guy what is exactly you are looking at. This 3 cross 3 is output of the last channel, right? So some kernel has convolved on top of this to give me this. So I'm going to ask that kernel that dude, that is the value I want. What 5 cross 5 you should be looking at? This 3 cross 3 output of 5 cross 5. And same is going to happen for all the channels. And finally we are going to be at the last image, and that image is going to be what you're seeing right now.
So this essentially doesn't solve the number of parameters and all the problems. Number of parameters for training the network, all will be seen.
Yeah.
But it's only solving the processing problem by parallelizing the.
It is reducing the number of parameters, because otherwise you need those many kernels to meet all these templates.
You are still using the number of kernels, right? I mean, we are increasing the receptor field
By going deeper.
By going deeper.
But using a thinner network.
No. If you don't have multiple GPUs.
This is what is happening right now. Imagine this is even taller. So you're going to this depth, but your kernel have to be wider. But when you're going deeper, your kernel length is going to be, the number of kernels you're going to use is going to reduce. You can assume the overall volume being same.
So when we take the example of what you have given, right? Identifying the A, B, C in a document. So the way we see it is, we need to identify, for each alphabet there can be 100 different representations. So for each alphabet you need to have kernels for each of the representations, and you need to have that for all alphabets. So let's say each alphabet has some 100 representations. To identify a document or the alphabets in a document, you need to have, let's say, 3 to 3 into 100 into 26. But I still need to understand how it reduces the number of parameters. And I definitely agree that processing will be faster because you're parallel.
Okay, now what we're writing right now, it's not true. Just try and understand again the emotion part. I'm going to take his example. We have 100 different kind of fonts in our data set, and we have 26 alphabets, right? Just thinking about that, we can say that we need 2600 kernels in the final layer, because I want to represent all of them. This is not true, by the way, because this is we thinking like human. AI is going to think that, okay, these two look same, why should I have both of them? These two guys can be manipulated by slight modification there, why should I have all of them, right? So and again, we are thinking in 2 dimension. Deep learning network thinking multi-dimension. It's going to think in 512 dimensions. So, but we are going to keep an example like that. This 2600 kernel is at the last layer. So you will have to build to that 2600. 32, 64, 128, you will have to go deeper. You will have to go literally wide to be able to target that. If you use a parallel architecture, you will not need these. You will only need 26. But you have to go much deeper. You will have to create more layers to be able to get that kind of receptive field where I can stack all of them. So here, the total number of kernels which are going to be required is going to be less. I'm going to show you also. There's a network which is called dense net. What is the least number of kernel you have ever used? The last assignment that where you had to add additional, maybe you used 10, right? And that was what? MNIST. If you're using ImageNet, you're never going to see anyone using less than 32. It actually expands, it goes to 1024 also. This network, which is called DenseNet, uses 12 kernel per layer. Every layer is 12 kernel, not one. Here you have 32 and 64, and we are writing the lowest one. When you use DenseNet, every layer is 12 kernel only. Imagine a 100 layer network where every single layer has just 12 kernels. Absurdly low number. Right, but we can do something. We can do something like this because of the parallel architecture. I'm going to explain that part also. Right? Give me like 10 minutes. Now look at this image. What are they talking to each other? They're talking about how the deep network looks at them, right? And what happens is that we have added some layers of convolution. And imagine that you are a kernel who's trained on a dog, but small in receptive field. But whenever the dataset came in, you always saw a dog with 2 eyes and a nose, right? But right now you're at an area where you're seeing 1 eye and a part of the nose. But you've always used to 2 eyes and a nose. What is going to happen is when the receptive field is not good enough for that particular part, and you're still looking at half the information, you're going to hallucinate. Right now our receptive field is too small, so if I is coming in, I'm able to draw it. The moment I go out from this layer, the moment I start adding more receptive field, I'll start hallucinating. I'll feel I'm actually looking at a dog, and the dog has 2 eyes. When you go back to the original image, it has 1. Right? And this is in the middle of the network. So as you add more and more receptive field, your network is going to look at the data coming in and will have a perception of what exactly it is looking at, right? These guys, and why is that going to happen? A kernel fires, and let's say the value is 5. The kernel gives the value of 5 because it is receiving these inputs from the lower layer, right? Now, if one of the channels is not there, it is still going to give some output, and let's say this output is 3 and not 5. But the layer after that knows that whenever this guy gives me input, it is generally based on those inputs. Whenever this guy gives me an amplitude of, let's say, x, that is generally based on those channels which are there. So if you go and ask the layer number 3, Was the second eye available in the layer number 1? It's going to say yes, because generally the second guy, whenever giving me an input, that has 2 eyes. So that is the hallucination which is happening in a network, right? So as you go deeper, the network is going to start imagining things. This is on a dog, we are training on a dog, and this is on the cat, we are training on the cat part. But look at the background also. Background is now becoming very weird. There's no class for the background, so it's going to hallucinate things which are not going to be important for our network later on. And the deeper we go, it's going to get better. Now the receptive field is good enough for me to see there was only 1 eye. So I'm not going to imagine a second eye. My receptive field is good enough to look at that specific area, right? And that is what we're doing here. Again, if you look at the background, the kernel looking at background, they are actually creating backgrounds now. They are creating these small mini gardens. But the moment you go close to your softmax, it is not interested in all of that. Softmax is interested in cat or dog. It is not interested in it's a cute cat or there's a background or not. It just wants those outputs, right? So finally we actually get something like this. The final kernels which are very close to your softmax are going to convert the whole receptive field to a single number. Imagine that you love someone a lot, but there's a computer which can say 6 for that love. This is what has happened. The deep neural network have learned throughout the whole data set is going to look at the receptive field. Finally, it is just a single number. That is what softmax does, and that is why when you use transfer learning, you are going to throw away the layers which are very close to softmax. Softmax was interested in this. We are not interested in this. In transfer learning, you are interested in this. In transfer learning, you want these latent vectors, these variables, which can take your image and divide that into smaller objects. We are interested in part of objects. We are not interested in objects. These are objects. Let me just give you an example. Name a character which can look like a tank and binocular also. Cartoon character which can look like a tank. It may have a binocular also. It may have some sort of piston-based machine. You don't watch cartoon? When you take this image, your deep neural network has never been trained on Wall-E. When you take this image and you take this image through a VGG network or a resonant network where tank and binoculars are one of the classes, tank and binocular channels get super excited. They give you very high activation, right? But if I wait for the last layer is going to say either a tank or a binocular. We are not interested in that. Let's say you want to classify a Wall-E as a cartoon character in your database. You're going to wait just at the point where we are getting a lot of part of object detectors. One of the object detectors is going to fire for the tank component. Another object is going to fire for the robotic component. Another object is going to fire for the binocular component. And we're going to take those vectors and we're going to, let's say, run something on top of this. Some sort of clustering mechanism where whenever Wall-E comes in, all of these vectors fire. So you can create some sort of cluster. We can do a PCA or maybe TSNE, or you can do some SVM training on top of that also. Not clear? Right? And for any object which does not exist in your database, let's say any class which does not exist in your database, can be broken down into some of the objects which your network is trained on. For example, I don't know which one to pick, which is the worst. Let's say it's the worst. I'm sure our network is never trained on this. But when this image goes through our network, it is going to find that this object looks very similar to one of the animal, or maybe some of the colors, or maybe because of some patterns or textures. So it's going to fire for that class. In fact, there is one, what is it called? Some components of this class might be there. So imagine a sloth without hair, blue in color, will give you something which is close to this. Right? That is where the transfer learning part is going to come in. Alright, so this takes us away from our, basically that closes the comment on the receptive field. We need many different receptive fields in our output because the object size is not same. And that is something which we can do easily with our parallel architectures.
Also one question about it. So you showed two images which look pretty similar, but Jadu is more like a blue colored one. When we do platform, the colors
Color will be
go
gone. Yeah. It will be some grey, some tinge of grey will still be character.
So even if you train Jadu images, ultimately both of them might look same, right?
No, the sloth will have the hair texture. Your Jadu will not have a hair texture.
But texture color will go in.
That doesn't matter. We are interested in the amplitude of the texture, whether the texture is there or not. Because if I depend on color, then cat color, there's no sync in that. So color is something we don't judge objects on. We judge on the amplitude. Yes. Now let's go back to the same example.
This hallucination will happen only in parallel.
This hallucination it will happen normally also. We're talking about receptive field here. So that hallucination will happen in normal networks also. This is 400 cross 400. Object size, edges, gradients, textures, patterns, part of objects, and objects. Let's say this is what we are trying to do, right? This is 200 cross 200. Edges, gradients, textures, patterns, part of objects, and objects. This is 100 cross 100. Edges, gradients, textures, patterns, part of objects, and objects. Right? I told you that we can connect it like this. Correct? This is specifically what YOLO did. But what we are doing right now is we are connecting internally. So I'm actually connecting, this is what? Edges. These are what? Edges. These channels are about to go here and convolve and become a pattern. Right? Edges are going to become textures, they are going to become patterns. I'm about to convolve on these channels and make them into a texture. Why should I repeat the same task here? Why can't I directly connect this to this guy? When these kernels are convolving on an image to convert those images into the textures, when as a texture kernel, I'm convolving on an input channel and I'm about to make them into a texture, I don't care about what receptive field they're coming from. Let's say you're a 3x3 kernel and you're convolving on a particular channel. Do you know what is the receptive field of the channel coming in? No, you're just looking at the channel. If the channel has something which you can find, you are going to find it. So what is going to happen internally is these guys are going to get connected, which means a dog of size 100 cross 100, which would have been identified here and had to be transported to here, is actually going to convert into an edge here, is going to go through the same route of other channels, is going to now convert into a texture and then pattern and finally a dog here. So you see how many kernels we have saved? You saved all of these kernels.
But by reaching at PA on the 400th point, your receptive field is much more higher than the...
No, receptive field 1 also, 3 also, 5 also, 7 also, 11 also, 13 also. So whatever receptive field you need, 1 cross 1 or 3 cross is going to carry forward that. That is the benefit of having a receptive field of 1, 3, 5, 7, 9 and all at the same time. Right? What I can do, let's say I'm looking at a very small dog, right? And that small dog, let's say that dog is 50 cross 50 in size. And I have another dog which is 200 cross 200 in size. And my kernel right now is going to convert the part of the objects of the dog into a dog. And let's say that is at a receptive field of 200. So this guy can do its job if the object looks like that or at the receptive field of 200 cross 200. My 50 cross 50 dog can actually wait using 1 cross 1 and then hit this particular 200 cross 200 layer and then get converted into a dog instead of getting convolved earlier and die off. Is this part clear? We don't have to convolve and convert our objects into our image features into objects immediately. That is something we are forced to do in sequential networks because there is no other alternative. Now I can take my objects, small objects, convert into an edge, and I can carry forward those edges till a texture has to be made. Then again I'm going to get smaller textures. I'm going to wait till I have to make that a pattern, and I'm going to wait then to make it a part of object, and then I'm going to make it an object. That is what parallel architectures provide you. So overall, you're actually going to reduce parameters. You're going to use less number of kernels as compared to VGG and other networks as well. Alright, now let's look at different networks, and we are again going to go deeper in that. So this is our VGG. You know the input size is 224. It is 224 because someone used 227. AlexNet is 227. So fortunately, we at least reduced 3 pixels. But you know that we actually use our network after 56 cross 56. right? So the first task of any DNN right now is to immediately hit 56 or 56. Right, Avenger movie has started, you have taken the first day ticket, but there's a huge line in front of you. You're carrying popcorn and all you want to do is to just go in. That is what is happening right now. So people have taken many tasks. For example, ResNet uses a 7x7 kernel. I'm going to show you ResNet in a while. It uses 7x7 kernel. But you and me know that if I use 3x3 thrice, I don't need a 7x7. Last year they released a paper and they said, yes, we can use a 3x3 and it actually reduces slightly parameters, less number of parameters. Right? Till then, it was very difficult for me to answer this question. The ResNet is using 7x7, how can you say that 3x is always better? Finally, last year, ResNet X, in the paper they clearly say that yes, we can use a 3x3 also. But you're in such a hurry, they don't care. Right? There's a small girl which is going inside in that theater with you. You're in such a hurry, you don't see that. I don't care, I want to go in first. So that's the hurry in which we are right now. And we add more layers and max pooling layers. And as you know, that finally we added these fully connected layers, which actually added much more bulk to the network. Now, right now you're looking at an inception paper. Now, inception paper looks at this dataset, which is ImageNet, and the problem they think which exists in this dataset is the size of the objects. We are talking about 2014 now. In 2014, receptive field wasn't there. Receptive field has started coming out in 17 and 18. This is a time when we think about receptive field. At that time, we were thinking about scale being a problem. That my object may be of different size. Indirectly, it is linked to receptive field, but the point of view is slightly different. We are thinking about scale of the object being different. Inception V1 thinks that there is a huge variation in the location of information. Now, location of information has nothing to do with convolution. Convolution and location information, they are like friends. Right? It doesn't matter that feature exists here or the feature exists here. I am going to convolve on the whole image. I am going to service every single pixel here. So the feature location doesn't matter to us, but that was a big issue for them. Right? This is a field which is now exploring and expanding. 2012 is the first time any network has actually came to mainstream, and we have started thinking on that. So we are still in the early days. This is 2013, getting paper published in 14. Choosing the right kernel size is tough. Right? No concept of receptive field. We are saying that I don't know which kernel size to pick. Should I pick? Because the size of the object is different. For a small dog, I need small kernel. For a big dog, I need big kernel. True. But now we know we can just use a 3x3 to handle all of that. Very deep networks are prone to overfitting. This is also true, and that was there because of the batch normalization not being there. Now, it is also hard to pass gradient updates. So to solve that, they added 3 loss functions using which I can directly backpropagate in my loss. Naively, like VGT, if you just keep on stacking, you will not be able to train. Now, they said naively stacking large kernels, large convolution operations. So they're not talking about VGT here. They're talking about a network with 7x7 followed by 7x7 followed by 7x7. But when you do this by 3x3, it at least gives you a breather to at least expand for 16 layers. So their solution to this problem, the problem they defined is, why don't you use kernels of different sizes? I'm going to use a 1 and a 3 and a 5. And I'm also going to make my network wider. I want to go deeper. Because I can't go deeper, I'm going to go wider. So that's the approach they picked. And they came out with this naive kernel. This is a naive kernel, and we are calling it a naive kernel because let's say I'm looking at input of 56 cross 56 cross 256. That means this kernel is going to be 3 cross 3 cross 256. So it's going to use so many parameters that there might not be any saving. So they actually changed it slightly. So that 56, 56, 256 is going to be convolved first by a 1x1, which is going to reduce the number of channels. Now I need a smaller 3x3. I'll use a 3x3x 32. And then whatever output is there, I'm going to concatenate that part. Right? So I have this 1x1, which is going to maintain the receptive field. I'll have this 3x3, which is going to increase the receptive field by 2. I'll have this 5x5, which is going to increase my receptive field by 4. I'll have this 3x3 max pooling with a stride of 2 to increase the jump. Right? This 3x3 max pooling right now is not a convolution, but it's like convolution also. It's taking the old channels and increasing the receptive field very fast because of the jump parameter in that particular line. So now if you calculate the receptive field of this network, it's going to be huge. We have jump in every single layer, and we had how many layers? 22 layers. And we had the jump of 2 in every one. So 2 multiplied by 22, that's the jump you're looking at. You'll have a jump of 44. The last 3 cross you're going to add will have a receptive increase of 88. Right? This is not what to do now. The receptive field formulas and receptive field notion were not there at that time. Going at a receptive field of 4000 for an image which is of 64 is not going to help you either. Right? You can't go to a satellite and from there you try and identify what car you're looking at. That may not help. You have to maybe fly at the height of a drone. Now, this network we already discussed. Then came inception V2 and V3. Now in V2 this said they learned from VGG and said your 5 cross 5 can be actually written as a 3 cross 3 followed by 3 cross 3. So that's one learning they have taken. Second learning they have taken is this guy, a 3 cross 3 followed by not 3 cross 3 but 1 cross 3 and 3 cross 1, the spatially separable convolution. So they added that. They wanted to reduce parameter more. If you get to reduce parameters more, what do? You add more layers or you add more kernels. So that is what these guys also did. And in Inception V4 they went mad. Please remember, Inception is designed by Google. Most of their architecture, their thought of AI is not that humans should be able to write a model. Their thought is the model should be good. What you're looking at right now is one module, Inception V4, where I have to use all of these guys. Look at the first guy. It is using a ResNet kind of connection. There's a skip connection which I'm looking at. I also have a 1 cross 1 which goes to yet one more 1 cross 1. That is weird. Then I look at 1 cross 1. This becomes a 3 cross 3. Fine. I have a 3 cross 3 followed by 3 cross 3. In another module, I have a 7 cross 1 followed by 1 cross 7. And the last module is also very different. There I'm actually concatenating or linearly adding these two different channels. These modules are discovered by something called grid search. Basically, you throw away many pieces of these together, many combination of these, and your network gets to decide after a period of huge Google computing power coming to rescue and allowing you to run for months that these are the 3 best ones which you have to use. Inception is world's best architecture. Inception gives you the best accuracy per model, per parameter, per computation use, but people don't use it. In the beginning of the session, I told you I'm biased towards ResNet, so you can already see my bias coming to you. Is this clear? Okay. Now, I can't use this Inception module because I have no idea which module should be placed where. I can't look at this guy and say that maybe 7 cross 7 should be used later on because the size of the receptive field is going to increase more. Maybe this 3 cross 3 should be used early on. There's no concept behind that. People also does not say that. People say use 4 of these, 5 of these, and 4 of these. It's defined by a computer. So what you're looking at right now is an architecture which is very beautiful, very strong, very powerful, but you can't customize it. If I want to train it myself, I have no idea where I should stack it. Either I should close my eyes and just download this model and just use it as it is, or train on my own data set. But that is sort of lying to yourself. You'd have no clue. And then people are going to say that AI is a black box. We don't know what happens inside the blocks because computers designed that. Let me compare with ResNet and then I'm going to comment back on this. ResNet, however, is designed by Microsoft and they actually thought a different problem. They told themselves that we need to go deeper. The intuition was there, but we were not able to pinpoint that intuition to a receptive field. So the idea was that we want to go deeper, but when we go deeper, we see overfitting. The deeper you go, the worse the network becomes, which is completely opposite of what should happen, right? So they actually asked a very simple question, and I'm going to ask this question to you. This is VGG 4 layers. If I add a layer in between, which does not do anything, if I add a layer in between which does not do anything and an identity layer does that, identity kernel is going to multiply with the input and give you the same output. So this is identity layer. It's not going to do anything. How many layers now I can add? Infinite. Now I can create an infinite layer network. Solved? Yeah. This clear? Okay. Now the paper says, okay, they are not purely identity. I'm going to do small work there. Just a small work. I'm going to change that layer a bit. If I do a teeny bit change here, I can go deep now. Maybe not infinite, but I can go very deep now. Right? ResNet is residual network. I will not add an identity. I just add a residue of something, which is going to allow me to go deeper. Is that clear? And let's look at the architecture. Their architecture is very simple. X comes in, I'm going to convolve on that X twice. So I need a 5 cross 5 kernel here. I'm going to get an output. I'm also take the same X and I'm going to add it to my convolution output. And finally I'm going to get f of x plus x. Right? This X comes in. It goes through here also. So this X becomes this and this convolution which I have done on top is here. Right? Okay. If you know the answer, then don't answer the question. If you don't know the answer, then try and answer the question. What is residue in ResNet? Your intuition tells you after looking at this what is residue? right? You're going to think this is the residue, which is not true. This is not the residue. This is the residue, right? Unfortunately, most of the images online is drawn like this. It is easier to draw. You just have to add a line, but you have to literally think of resonate like this guy. That your highway is the main sacrosanct place. Your X line is the main line, and you're adding something to it. Is that clear? That is how you have to think about resonate. Let's go back to this image again. Okay, what we are saying right now is my f of x is not going to add a lot of detail. F of x is going to add only a small bit of detail. If f of x is only adding a small bit of detail, then I can go as deep as I want. That is what they're trying to say. And they are saying that because I am carrying forward my x. Because I am carrying forward my x is so large that whatever x can capture is going to be very small in the detail. That means I can actually go back. Now, if I look at my resonant module and it's shown like this, I can actually get my loss function here as we discussed in the beginner section, and I can pass on my gradients as long as I want. But clear? So we are not using identity layers. This was supposed to be an identity layer. The mathematical proof what resonant has in the paper is for the identity part. They're saying we are very close to identity, and they share some examples also, which examples are not scalable. Example says that I have this image coming as x, and let's say I want to find out x. Value of 4 comes in and I want to give a value of 4. If this is one of the problems I have to solve, all I have to do is to make sure my f of x is equal to 0. Right? If x is equal to x plus f of x, my f of x has to be 0. So this is one of the things which they have explained in the paper, but we are not going to go in that mathematical direction. We are going to stick to our point that this allows us for us to pass on the same channels and actually pass on the gradient back as well. If you now think about your resonant module like that, and you look at the resonant module on the right side, the first pool layer, let us say that it's not there and we are looking at the image, right? The first convolution and the pool operator is not there. So let's say we are looking at the image. Is the last layer seeing the image now? It is seeing the image. Is some part of the image still there? Of course, I'm adding some data on top. I'm destroying some of the pixels, but I get a very good view of what the original image is. Right? This is a very simple architecture. Every time I'm just adding one more skip connection and just continuing to add further. Now let's break down the architecture. You see the first 7x7 kernel. They're in a hurry to immediately get rid of your 224 and arrive at 56x56. And right now we are at 56x56. Right? It's very similar to VGG. So this image actually explains that we start with VGG16, we convert that into a 34 layer network, and we add skip connections everywhere. Now our image of 224 starts here. After that we convert that into 112, we do max pooling, it becomes 56. 56, and this is also 56. So we are using padding to make sure that all the blue channels have same size because I'm adding these guys. Now you see the green channel, the first operator is stride of 2. The first thing we are doing is a stride of 2, right? Now we discussed max pooling, convolution followed by max pooling compared to a model where we are doing in the stride of 2. Max pooling is going to be much better in accuracy. Stride 2 is going to cause checkerboard issue. The resonant does cause checkerboard issue. But what they want is to keep a model very, very simple. They want the model to be just simplest possible model on earth. And they want to keep the parameter count also low. If you keep the parameter count low, you can add more stuff. Right? And that is why they are using a 3x3 with a stride of 2. Now, if you do a 3x3 with a stride of 2, we discussed we are going to look at less number of pixels. Instead of looking at each pixel 9 times, I'm going to look only 4 times, some and 2 times some other. So overall computation also going to be less. That is their idea of keeping the model simple. And they're adding the channels, they're not concatenating them. If you concatenate them, your 32 becomes 64. So next 3x3 is going to be required to have 64 channels inside. They're keeping the model very simple and efficient from their perspective. Right? Is the part clear? So the problem right now is I have a channel size which is coming in as 56. Right? This is coming in as 56 x 64, whereas I have just converted that into 28 x 128. Now I cannot add them. This is not possible. If I want to add, the pixel, the overall channels, all the elements basically must be same. So x-axis, y-axis and z-axis must be same, but I can't do that right now. And that is why this line looks slightly different from this line. right? This line is actually converting our 56, 56, 64 coming from here into a 28, 28, 128. How can you do that? How can you convert this guy into this guy? One single step. In one single step, how can you do this? How will that reduce the size of the channel? That is why it's a very big, the moment you will hear the answer, you'll be, I think, happy. Happy is the feeling you should get if I show the answer to you. And the answer is a 1 cross 64 cross 128 with a stride of 2. If you're not happy looking at the, on the solution, you're not geeky enough, you're not CNN enough right now. Such a simple solution. We are going to use a 1 cross 1 with a stride of 2, which means if I am convolving on a 6 cross 6 by a 1 cross 1 of a stride of 2, I am going to get a 3 cross 3. And 1 cross 1 also allows me to merge channels and make or increase them or reduce them. So one simple operation which actually allows us to convert our 56, 56, 64 into 28, 28, 128. The part clear? And that is what we are using in our resonant module. So I have a need to convert it here. I am going to have a need to convert here also. That is also 1 cross 1 with a stride of 2. And in the last time I have a need here. Now what you're seeing right now are 4 colors. There's a reason we have 4 colors here. We have blue, we have green, we have pink, and then we have blue again. Right? The purple and blue if you look at the color closely. But I wanted to count the number of lines there. 1, 2 and 3. These are 3 resonant blocks. Right? And the green has how many? 1, 2, 3, 4. How many do we have in red? 6. How many we have in the last blue? 3. So what you're looking at is 3, 4, 6, 3. And why is that important? When you write a resonant code, inside that all we have to say is 3, 4, 4 or 5, 6 and 3. The moment you say that, you have just made a resonant 34. If you say 2, 2, 2 and 2, you get resonant 18. Resonant 18 or 10, I don't remember that, but you basically just define these things and you'll be able to convert it into a newer resonant module. So when you hear resonant 18, resonant 34, resonant 50, resonant 121, all you're doing is change these numbers. In 4 blocks, we have different number of layers inside that. Is the part clear? And you should be surprised also, in fact not surprised, that there are 4 blocks we are talking about. Edges and gradients, textures and patterns, parts of objects and objects. Human brain has 4 layers. There's the first session I shared with you also. We have V1, V2, V3 and followed by IT or V4. Right? Name might not in sequence, but this is the same architecture which we are also trying to follow here. Is the part clear? Alright. Now as I told you, so this is the original architecture which we used, the one we are discussing right now. In the original paper they added ReLU here. So this is the original architecture, your X is flowing through this, but they added ReLU here. Right? Now we just discussed, that line is very important for us. This is like sacrosanct for us. You're not allowed to do anything there. But in the first paper they added ReLU there. Resonant is also improving. Resonant 1, Resonant 2, Resonant 3. So this was the mistake they had done in the first one. Now why ReLU is a mistake there? I am backpropagating. You have done ReLU on me. I was carrying information to carry it forward and you have just destroyed because ReLU derivative is 0 or 1. So at some pixels where I wanted to give a feedback, you're just multiplying with me with 0. So I cannot pass on my feedback. And that is the most important line. You're throwing away half my values and I can't propagate back. So we fix that in the next architecture where we actually use this full pre-activation. We are calling it pre-activation because I'm doing batch normalization before the convolution in this layer, or it looks like that. Right? But we have moved everything away from this line. There's nothing on this line. This line is going to be a sacrosanct highway like Uberbahn in Germany. You drive at 160 km an hour, you get a notice. You need to drive faster. Uberbahn has a lower speed limit. In India, we have an upper speed limit. Right? That is this road. You are not allowed to touch this line. So if someone asks you a question that in the skip connection, if I add a 1 cross 1, would the accuracy reduce? Of course it will reduce. And we have one skip connection already. We are adding a 1 cross 1. So we need to use less of that. That is why we have only 4 blocks also, right? But everything is going to be moved here. Now you're thinking about adding a dropout. Where are you going to add dropout? Here. You're not going to add dropout here. This is going to be pure for you. Is this part clear? Okay, now exception, inception, dense nets are better than ResNet, right? Then why do we love ResNet? I'm using V because I'm hoping you're already biased by now. If you're not, then why do I love ResNet? Imagine a computer which you can buy at 50,000. Computer has 64 GB of RAM. It has 4 TB of hard drive. It runs Windows 10 at the super fast possible speed. It is light, only half a kilogram. It has a battery life of 4 days. But the keyboard is Russian and the operating system is also Russian. That is what Inception is. Everything is good about that. But it is not changeable. You can't change. It is not dynamic enough. It is not flexible enough for us to go and modify that. You want to use Inception as it is for object detection, detecting a dog, frog and other stuff, you can just download and use it. The moment you decide you want to train it, the hyperparameter tuning, the tuning of those blocks of it, they should come is very difficult. It is designed by a computer. And computer can do it. Computer can run multiple times and figure out those hyperparameters, not humans. ResNet on the other hand is like a MacBook. May not run for 20 days, but one day it will definitely run. Right? And it will not fail you. When it will fail you, it will definitely fail you. If the battery goes off, it will go off. Henry's law is with you. Murphy's law is with you. But it's not going to disappoint you. May not run as fast as Windows, but it will not get heat up and it will not close down like Windows also. Right? I have a huge bias towards ResNet. I find that model to be very easy to understand and implement, and I hope you decide on your own that which bias you should have, and you should have bias towards ResNet, even though you are free to pick any network of your choice, but if you pick a ResNet, it's going to be good. It's cool? Alright.
Why would you put DenseNet?
DenseNet also, so DenseNet we have not covered. DenseNet is a very different kind of architecture. We don't have time to cover DenseNet, but in DenseNet we connect every single layer to every single layer. Right now what we are doing in ResNet is we are doing the skip connection, right? Imagine we have a block and inside that block we have 6 layers and we connect every single layer to every single layer inside that. That is what DenseNet is. It's very similar to human brain. DenseNet is state of art, but the problem with DenseNet is it takes so much RAM that you can't train it. A DenseNet with a batch of 32 is equal to a ResNet with a batch of 512. It is very slow to train. So if our hardware can support it, if NVIDIA tomorrow comes out and says my graphic card is 64 GB, then we may possibly can use DenseNet. But from an architecture point of view, DenseNet is also very simple. It follows the ResNet philosophy, but RAM uses so much that we can't train it. It's clear? Okay, now we're going to move to image augmentation.
So between ResNet versus DenseNet gives you better result?
Exception, inception, DenseNet, all are better than ResNet from the accuracy point of view.
From object detection.
From object detection accuracy point of view. But you're going to see that everyone still uses ResNet. Okay, now what we basically are saying here is, look at this table. You're seeing mean AP on the left axis, which says mean average precision, which is how good your bounding boxes are as you're training. Right? A higher AP means a good overlap between the actual bounding box and the bounding box your network is predicting. That is what we are looking at, IOU, intersection over union. And on the bottom side, you're looking at the images. What this graph tells you is that if you want to increase your accuracy by X units, and you increase the accuracy by X units by using, let's say, 10 images, the next X will not be because of 10 units, it's going to be log of that. It's exponential scale. So if you use 10 images, maybe you have to use 100 images. So a 1% increase by 10 images, next 1% is going to be by 100 images, next 1% is going to be by 1000 images, next one is going to be, and so on. It's an exponential relationship, and we cannot work on this kind of relationship. That means your database is going to be 1 billion images. That is something we cannot do. We cannot get those kind of images. Is part clear? And that is why we do data augmentation. The moment you do data augmentation, image is slightly different, and that is all we need. The way you have to think about data augmentation is, first of all, we are interested in trying to figure out what exactly is the gradient of our loss function. Now, if I draw just one point, if I just draw one point and ask you what is the gradient here, we can't answer. We need at least 2 points, so I'm going to draw one more point here. Now I can actually draw a line between them, and that is going to be my approximate prediction of how the loss function should be. But the moment I do image augmentation, I'm going to draw this image, flipped image of the same image. The moment I do image augmentation, I'm going to just do some random crop of that particular image. I'm going to brighten that image. I'm going to, let's say, add jitter to that image. Right? I'm going to, let's say, merge 2 images. So when you keep on doing this, you actually are able to define your loss function, and your loss function has much better prediction for the images it has never seen. That is what is happening when you are doing image augmentation. And we are going to use, in fact, you're going to see that most of the network, in fact, nearly all the networks follow one simple policy for the data augmentation, and that is sort of fixed. First, you're going to take your image, you're going to pad your image by some pixels, right? My image is, let's say, 32 cross 32. I'm going to pad my image by 4 pixels or 8 pixels on sides, and then I'm going to crop it 32 out of this guy. That is the image I'm going to take. Right? What we are doing is that I'm going to take my image, I'm going to pad my image now looks like this. This is padded image, right? And from this image, I'm going to crop some section which is the image size I need. And this is a random crop, which means dog or Iron Man is not going to be at that location whenever you're cropping. It's either here or here or here or here. Every time you're going to do a random crop, it's going to be a slightly different location. So every time you call your image, it's going to be a different image. Slightly different image, that's what we need. First augmentation you're going to add. Second, you're going to say that I'm going to randomly flip this, which means sometimes it's going to be horizontal where x and plus x, and sometimes it's going to be a flip of that. So it's going to be minus x and x, right? So your cat will not face any issue, right? We can do this for cats, dogs, and other objects. We don't do this for face recognition. A flip face is not the same face; it's a different face, right? And dog will not get angry if you use a flip face for that dog. So for objects and for our simpler data set, we flip that. Now our image is certainly very different. Randomly it's going to be flipped, and I'm actually cropping some of the area. And we are going to use something called cutout. I'm going to explain what that cutout is in a moment. So we are going to crop a part of the image and throw it away. Right? That's an image augmentation we are going to cover. So you follow these 3 steps, and this is the three steps which is followed by nearly every state-of-art network. Alright. These data augmentation policies are called PMDA. What is PMDA? Poor man's data augmentation. That is the actual term, and we use this term to tell us that we are not applying a brain. We are just using some random policy and just applying it. There's nothing special which we are doing on top. Right? Now, in the actual course, I have extended this. I have extended it to something called middle class data augmentation, and there's something called rich man's data augmentation. Right? One good example of rich man's data augmentation is Google. They trained a reinforcement learning model to figure out what data augmentation policy should be used. Their reinforcement learning model took 17,500 GPU hours to train, a network which takes 1 hour to train. You understand why it is rich man's data augmentation? You're going to run a reinforcement learning model which is going to try every single possible augmentation strategy and then come out with the best strategy which you'll use to train a network for an hour. Fortunately, that the augmentation strategy mentioned there, you can directly use it because they have defined it for a specific network. Then there's another rich man's data augmentation policy where you're going to train a GAN for months to create data which looks like your data, and then you're going to train your network on this data. So these are called rich man's data. We're not interested in that. We're interested in middle class men data augmentation, where we possibly fall. And one particular augmentation policy which falls in this and stands out is called cutout. Cutout is ReLU of data augmentation. When I say ReLU, that's a champ basically. This is the iPhone of data augmentation. Why do we say this is iPhone of data augmentation? Any new augmentation which comes out compares itself with cutout. Everyone is trying to beat this guy. If this happens for 3-4 years and the top leader has not changed, that tells you something. In 2015, 16 we were comparing with this, 17 we were comparing this, the whole year we compared with that, 18 we compared with this, 19 we are comparing with this. And policy is very simple. I'm going to take an image and I'm going to throw a part of that image out. I'm going to start with the image of, let's say, 32 cross 32. I'm going to throw away a part of 16 cross 16 out of that image. Any random. I'm going to explain the algorithm, but this is what we're doing right now. And I'm going to color that with the mean of the data set. If I added black, the mean of the data set will change. So we generally throw back the mean of the data set. So the color you're seeing is the mean which we calculate. Mean is going to be grayish, right? That is what you're seeing right now. Is the part clear? I want to show you this image, which is here. Right? The red guy. You see the box is not complete. It is not inside the box, right? It's outside. And in fact, in the black one, it's also bottom. So it is possible that my cutout section might not be in the image. And that is why I want to share exactly what cutout does in terms of algorithm. This is the image I have. the image happens to be 32 cross 32 in size. The first thing you're going to do is to notionally you're going to scale this image by 16 pixels on all the sides. So my image now becomes a 64 cross 64. Now I'm going to crop a region of 16 cross 16 randomly. So it may lie outside also, which is something we need. We want our data set, we want our model to see the real image also sometimes. But I'm going to fall somewhere in the image also. Now I can cut out the tail of the airplane. I can cut off the leg of the penguin. I can cut off the head of a bird. I can cut off the right hand of the man, and so on. Now my network is forced to predict that without the head of a turtle, the rest of the shell also can be looked at and classified as a turtle. I can look at the legless penguin and still classify it as a penguin. I can classify the headless bird as a head. That is why this actually increases your performance by a lot margin. There's something called gender bias which is there in the network, and if you look at the paper from the cutout, let me just open that quickly for you. Okay, this is the cutout paper, came literally last year, 2017 November. It's not in this paper. Okay, so I'm going to show it again. There's another paper which refers to this particular paper. It's called GradCam. Is the part clear what we're doing here? Right? Okay.
Is it a regularization technique?
Every single data augmentation strategy is a regularization technique. So this is a simple one, and these are results, and of course the results are good. Now we're going to talk about global average pooling. Global average pooling we have discussed. We'll not take our 7x7 requirement to and flatten route and that fully connected layer. I'm going to use a global average pooling layer, convert that into 5 and 2 numbers, and then those numbers I can use the FC after that to increase the capacity. That is what we have discussed, right? Now we use global average pooling. It is because it's much more native to convolution. If you are using gap in your network, the image size can be anything. You are not forced to give any size. Let's see why. Let us write VGG network. VGG starts at 224, goes to 112, goes to 56, 28, 14, 7. At 7 we are at, let's say 7 cross 7 cross 1024. Right? First thing we are going to do is flatten this out. I don't want to calculate this guy, but this seems like 1000, this seems like 50. So there are 50,000 numbers here. And I'm adding, let's say, after this 20,000 or 2,000 parameters. Those are the weights which are linked to each other. Okay. Now the size of the image changes. Let's say the size of the image is 400. So 400 becomes 200, becomes 100, becomes 50, becomes 25, becomes 12. So now 12 into 1000, 12 into 12 into 1000, which is 14400 numbers are coming in. My model is going to crash now because I am expecting some certain different numbers and some certain different numbers are coming in. But let us say our network was not that, but like a ResNet, I had 112 and then 64, 56, 28, then I had 14, then 7, and I had used a gap here. Right? Gap is going to convert whatever is coming in 7 cross 7 cross 512 into just 512 numbers. Now let's send to 400. 400 becomes 200, becomes 100, becomes 50, becomes 25, becomes 12, becomes 512. So you see, your non-network, these kind of networks are called fully convolutional networks, FC networks. Sound similar to FC layers, fully connected layers, but these are FC networks, which are called fully convolutional networks. Now the size of the image doesn't matter. Whatever size of image you're going to send in, it's still going to process that. Is the part clear? We want our networks to be something like this. And gap does not cost us a dime. There's not even single parameter which is used to maintain or to be learned to handle a gap layer. Right? There's no parameter which is there for the gap, so that is why we're going to use it. Now we covered gap because I want to cover something called class activation maximization with you. We want to figure out exactly in the image which pixels were responsible for predicting our object. Let's say that's the problem we want to solve. So we can solve that by something which is called class activation maximization, and we solve it by using a particular formula which is called GradCam. Right? Now GradCam is applicable for the data sets for if you're using a gap image. Okay, now I'm going to show you a simple demo of what it can do. The video unfortunately has no audio, so I'm going to play an audio for you. This is a very simple video, just get time, it's a 2-minute video. So what you saw right now is that we can actually search for a class. We can specify the color and it will actually identify that particular part. The whole video is actually fascinating. Inside that you can actually write text, horse standing next to a house, and it will actually find that also. But everything starts with a very simple use case, a very simple example of what we are going to cover. Now what you're looking at is the GradCam algorithm, and I'm going to explain how do we use it. Okay, this is the image we are starting with. You're sending some image to your deep neural network. This network happens to be our network, which is gap based and not something which has FC layers. This is the network the image is going through, and we are interested in the channels which are close to the output. Now these channels must have slightly higher resolution. When I say slightly higher resolution, these cannot be a 1x1, these cannot be 2x2, these cannot be 3x3 or 4x4. You want a gradient map. I cannot create a gradient map with 9 pixels. If you have 3x3, this is not a map, that is just a one block which is lighting up, one of the 9 possible positions. You want a gradient, you want the heat map. Heat map has to be fluidic. It needs to look like a heat map. If I have just 1 pixel, if I just use 1 pixel, how many colors I can add in that 1 pixel? 1. So heat map is going to look either red or blue. And that is the problem you're going to face when you are going to write your own model, because you're going to forget that you need to implement GradCam on a channel where the channel size is large. Now this channel has to be close to your output also, so you cannot in your network define that because my channel size is 1x1 I cannot use it, so let me go back. If you go back, when I say back, you're going to, let's say, go to the 6th layer instead of 9th layer where you have a 7x7. You're not looking at classes there, you're looking at part of objects or maybe patterns there. So the whole image is again going to be a blue image or green image. We need to be close to our outputs. We need to find out channels which are responsible for the class output. But clear? So this you need to make sure is at least a 5x5 or more. Okay, we have made sure that is happening now. Now I have a gap coming in, and after that I am predicting my classes. Now the class we are predicting right now is tiger cat. That is the class which we are predicting right now. Okay. Now let me take one of the channels from here, and I'm drawing that channel here. Please tell yourself I'm drawing a 5x5 or 7x7, and I'm interested in that pixel. I'm going to draw that pixel here. If this channel is important to predict this particular cat and I change this pixel value, I should see immediate effect on the output of this class. Is it clear? That is called gradient, a derivative. If I do derivative of the value I'm getting here with respect to the pixel in the channel, and that channel happens to be an important channel, I'm going to see a big positive value there. My derivative is telling me don't change that value, it's very important, it's positive. This is clear? And if this channel is negatively linked with my class prediction, this channel is for a tire and we are predicting a cat. If I increase a pixel value there, this is going to reduce now, so this is going to be negatively linked. The derivative right now is telling me don't increase that channel because when you do, my cat prediction is going to go down. Is that clear? So what we are going to do, we are going to take a derivative of every single pixel in the channels we have with the class we have predicted. So DC, the class prediction, divided by DP, every single pixel we have in a database, right? We have in that particular layer. And these are the channels I'm going to get. If this channel overall was important for the prediction, the overall pixel values are going to be positive, or wherever the feature was found is going to be positive. If the channel was not important, overall pixel values are going to be negative. But I don't want to play with these 49 values. Let's say there's 7 cross 7 or 5 cross 5. There are 25 values there. I don't want to play with that. I'm going to do a gap on this now. I'm going to do a gap on the derivative layers which I've figured now. Gap is what? Sum of all the pixels divided by the number of channels. If the channel was important, the derivative of the pixels is going to be positive, and the gap is also going to be positive. I'm interested in that one number. So that gives me which channel is important and by how much. If the channel value is very high, that seems like a very important channel for me to predict that specific class. If the channel value is very low, which means that channel is inversely linked to my class. A tire with a cat, right? A buffalo, let's say a leg of a buffalo for a car. So these are inversely linked channels and they are going to get a negative value. Are we clear till here? How did we get this guy? Right? Now we are going to do a very simple stuff. I am going to multiply each of the channel where these values are coming from with the value itself. There was a cat channel. That cat channel was firing already. I have now multiplied with a very big positive value. So the channel is not very happy. All the values are like skyrocketing. And the channels which are not important, I am multiplied them with a smaller value. So now they are negative. After multiplication, I'm going to add all of these guys. The first step is adding all the channels together. So whichever positive values were there, they're going to come on top of each other. 5 cross 5 cross 512 is now going to become just 5 cross 5 cross 1. I'm adding in the z because I want which pixel is important for me. So I'm going to get a 5 cross 5 cross 1. Then I'm going to add ReLU to throw away the negative values. I'm going to scale whatever this channel was there and I'm going to overlay on top of my image. Alright, let's look at the code. It's actually very simple to implement. Okay, this particular code has many codes, so we'll have to scroll down. It's a collection of different codes which I want to share with you. This is a GradCam implementation. We are picking a VGG network, right? Because this is a VGG network, I can't play with the fully connected layers. Whatever I'm going to do with the 2D channels. After that, I can't do anything. I'm going to read this image from internet. After that image, I'm going to resize it to 24 to 24. Why do I have to resize? VGG has fully connected layers. Otherwise, I would not have to resize. But VGG has fully connected layers, so I have to resize it to 24. I'm going to do now a predict equal to model.predict. So this is the predictions I have. I'm going to take an argmax, which is going to tell me that the biggest class which is there, which is going to be whatever object which we have found in the image. I'm going to print the class ID which says 180. I'm going to use that ID and I'm going to get that specific layer. I'm interested in my block 5 column layer. I know the name because I've done model summary for VGG. After going in that specific layer, I'm going to calculate the gradient of this particular layer with the class output I have calculated. With the class output I got, 180th class. That's the same line, the derivative part. I'm going to take a mean of these guys to make sure they are actually within a specific range. And I'm going to pool them, which is basically adding them together. And I'm going to make the output, this part is fine. This is the multiplication of this, the value itself with the channel part. We've done that part as well. We're going to normalize it to make sure that the values are between 0 and 1. That is what OpenCV can show. And I've done this, the mean part with respect to the Z channel. Basically, I have 512 channels. I'm collapsing that into one specific channel. So I finally get 14 cross 14. Now 14 cross 14 is a good resolution. It has many pixels. Now when I take this image and superimpose with this dog, I'm going to get this. Right? And the moment you see such an image, first thing should hit your mind is how cute the dog is. No, this is a disease you're seeing right now. And the disease you're seeing right now is your network looks at the face of a dog and then says it's a dog. That is not a good thing. Which means if dog holds a frisbee or it's holding some other object in the mouth, the prediction is going to fall. How do we fix it? Cutout. When you now implement cutout, many times the face of dog is not going to be shown to the network. It has to figure out dog with the body. And that is why I was trying to open this paper. I hope it opens. Okay, so now in GradCam we can see these results clearly. Alright, now I want to quickly jump. So these are all our channels you can play around with, and if you, of course, if you're going to pick initial few layers to do this, you're going to see the whole image is colored because edges and gradients are used for all the classes. Okay, I want to show you something which may interest you, and you may actually want to solve such a problem in future. Alright. Now the image on the left side is a nurse. The image in the middle is the predicted class and it's a nurse. Nothing wrong there. But look at this second image. The image is not a nurse, but the image is a doctor. But the class prediction now is the nurse. And in both the cases you can see that the model is looking at the face of the person. Because of the less sample in a database, the model has learned that female are always nurses. And this bias is not in the network, this bias is in the database we have. Like if I ask you truck drivers are, the bias is there. But we don't want that bias to be there, right? We want to get rid of that bias. The moment you add cutout to this, you look at what your network is seeing in the image. Your network is looking at a stethoscope and is looking at the color of the cloth. If the color of the cloth is not white and the stethoscope is there, possibly a nurse. If the color of the cloth is white and the stethoscope also exists, possibly. Look at the third image, a very clear example of where the network is actually looking. Network is looking at the face and then saying it's a nurse. But clearly she's wearing white and the stethoscope is also there. The moment you add cutout, it will be forced to look at the stethoscope and other objects which you can see to identify that as a particular doctor and the color part also, and then predict it's a doctor. Right, so cutout and GradCam, these are the two diagnostic tools you have for DNN. We don't have a model where or an application where you run your DNN is going to come out and say your model is not doing this because of that. We don't have such tools. So you have to use GradCam and you have to use cutout in your own data set. The part clear? Okay, now this we have done, this I explained. Now assignment. You have two assignments. One assignment is called assignment 4A and the other is called assignment 4B. When you click on this specific link, file, it is going to download a zip file. That is the zip file. When you open this zip file, you're going to find a folder. When you unzip that folder, this is the VIA HTML file which is there. Click on that. It's going to give you this UI, right? But because this HTML is not a proper application, the stuff is not loaded yet. So I have to go to my project and I have to click load. I have to go to my same assignment 4 folder and I have to upload this project file. You have to manually link it. The moment I manually link it, it's saying the image is not found now. So now I have to go back again. I have to add files in the same folder. I have to go in images. I have to select all the images, Control A, and I need to click open. Now it is properly loaded. So each one of you will be emailed on Monday a separate folder of 100 images. Right? This is the first time I'm trying to do this. Till now, whenever we actually worked on EIP or in fact EV other courses also, database is someone else's, model is someone else's, we train and we target a particular accuracy. But this time we are trying to do something different. I'm trying to tell you how do you create your own data set, how do you link it to your own model and then train the hell out of it. That is the objective right now. And along with this, I also want to do some sort of social measure of how we think about people. Look at the task here. What you have to do is to basically find an image, and you're going to do it for me. You're going to click this rectangle and I'm going to highlight the face. We are highlighting the face because the final model we are going to be releasing, we are going to be blurring out all the faces. We don't want the faces to go out. But as soon as you do this, you're going to get this box. Click this guy, which is going to send that box at the bottom. We don't want to hover around because I have a touch screen, I can move in left and right. You may not be able to do that. What is the age? What is her age? How much? 35, 45 or 25, 35? Let's say we click this, right? What do you think is her weight? Is she underweight, normal, healthy, slightly overweight, overweight? Normal, healthy. Gender? Female. Economy class. Let's first see the options. Lower middle class, upper class, uber upper class. This data set is going to judge you. And believe me, let your judgment come out. Because when the data set is mixed, it's going to be, of course, anonymous. Will not be able to figure out that whose judgment is coming in. I want to capture how we think about people. Right? When you see many images, you're going to see, yeah, she's wearing a watch, she's carrying a bag in front. Generally, that's not how underclass people do. You need to feel confident to do something like this. Right? Maybe let's say we still stick to middle class. Education. You know she's educated, but you also know she's not overly educated for some reason. I'm trying to capture that. How do we actually do that part, right? So we are going to say educated. Carrying a bag, yes. Which bag? She's carrying a daily office bag. Now, is she wearing earring? I can't see, but I can see some jewelry, right? And that's a jewelry. I clicked, it's a wrong link. That's a sunglasses. Watch, of course she is, right? And footwear, I can't see, so I can't see. Demeanor, right? Demeanor is something which actually explains a lot about how we perceive humans. Right? I'm just going to show you an example. You're never going to see a millionaire or billionaire, at least in your head, standing like this. So demeanor actually captures how we feel about people. If someone is actually standing still, right? The shoulder also stooping down, or not stooping down, they're stressed out. You feel that they are from a separate different class. Now, if you look at this image, what demeanor options do we have? I have average, classy, groomed, unkempt. I think this is average. This is not unkempt. This is not unkept. This is not classy either. Now, clothing style, that is going to be average, fashionable, or below average. Average, right? Image quality is not a bad image, it's a good image. You look at other images first, and then you figure out which is bad, which is good. It's going to be subjective. Emotion, she seems happy. Clothing style is daily, sports, formal, or ethnic. That is where most of you are going to split. Right? Ethnic clothes are slowly coming into mainstream, and we are calling them daily wear. And daily wear, some daily wear is actually going back into ethnic. Sari used to be a daily wear. Now it has gone back into ethnic, and that changed. That is how society is actually changing right now. So we are going to say this is a daily wear. And the last option for us is body pose. And body pose is frontish. You are basically looking at the shoulders. You're not looking at the face. Right? So this is a frontish part. Now you're going to go to third image, and you're going to do the same thing for her. You can't see her face now, right? But you will still be able to have your own judgment about whether she is educated or not, whether she belongs to a high class society or low class society or not, what is her age. You will still be able to do it, right? So in this data set, we are just basically trying to do that. And finally, we should hopefully be able to publish a report that most of us think if someone is fair, they are rich. Some things are automatically going to come out. So I just want to capture that as a fun part. And what you can do for your own models is basically, okay, first of all, let's still focus here. Once this is done, you need to make sure that you are saving your project. So click save. You are saving the project file right now. And when you click OK, you are basically going to be saving this file. Assignment for project J, right? You can overwrite it if you want. Okay, that's the first step. Second step, just to make sure you have saved your file properly, you're going to go in annotations. You're going to export them as JSON. When you export them as JSON, you're going to save another file, and that file, let's say we call it via export JSON. Right? All the annotations are saved in JSON right now, so that's fine. And when you go back to your GitHub, you're going to upload your zipped folder, your images folder. You're also going to upload your JSON project file, and you're also going to upload your annotation file. All of these must be inside a folder which is called assignment 4. Now, what we are going to do is the next assignment is going to be 2 weeks long, the assignment 5, and that is going to be a classifying assignment. So I'm going to wait for a week when everyone is submitting a dataset, and I'm going to upload them, convert to a format, and share it back with you. You are going to be training your model on that dataset. So I'll give you a base model where that dataset is already linked. So we'll know how do we collect dataset, how do we combine that into one single file, and how do we connect it to the data we want to link on. So that model is going to help you understand that part. Assignment part B is this assignment should not take you more than an hour. But please don't do this on a tablet or a phone. Pick a laptop or pick a desktop because you need slightly bigger screen for this particular assignment. Right? Each of you are going to get 100 images in an email. Yours from Saturday batch, you're going to get this on Monday. The Friday batch is already received. Right? So 1 hour an assignment, so you don't have to struggle a lot. What you're going to do for the assignment 2 is you're going to open this folder. Now you're going to open this link. This is the CIFAR 10 explained on Keras. Resident model explain on Keras, right? You're basically going to copy paste it on your collab. You're going to take the CIFAR 10 dataset. You're going to train it for 50 epochs, and you're going to cross a 88% validation accuracy. Right? You're going to show GradCam results for 10 images. See, Resident by default is going to go at 90. This should not be hard for you. right? ResNet by default, if you train it for, I'm asking 50 pops because I wanted to add cutout and other things also to make sure that you understand how to use them. We discussed, right? Random crop, then we are going to do horizontal flip and cutout. The moment you do that, it's going to hit 94 also. But you have to train it slightly in a different way. So 88 is not a hard target here. The assignment is actually asking you to understand how to use ResNet, done, and show GradCam result for 10 images. And that code is already there. This is how we use GradCam. So you're going to integrate this back to your dataset. You're going to pick any 10 images. You're using a ResNet. There's no fully connected layer. So these images can be internet downloaded images also, or some of the images from the dataset of CIFAR 10. But think about that. If you take outside image, how it's going to look like. Like have some sort of curiosity in your brain. You can test some different images. You're going to upload this on GitHub and assignment 4B inside a folder assignment 4, and that is the whole thing you're going to upload. Part clear? Any questions you have?
Why are we so concerned about receptive field while calculations? But because when you say as we cross receptive fields, as the receptive field grows larger than the size of the image, it is actually getting better. So why are we so concerned? Why were we so concerned during the assignment about calculating receptive field?
Now, this is your accuracy and this is your receptive field, right? That is the size of the image. Your network is going to follow that kind of line. It's going to overshoot it and then it's going to follow. We are talking about receptive field because we want to figure out what is this guy.
We want to be slightly higher than the receptive field, but
not too high. The moment it go too high, this is where the overfitting is going to start. Right? We did not specifically cover this particular point, but maybe in the next session I'll get more time to share this part also. If you go very deep, for example, take VGG network for CIFAR 10, not going to work.
In the image related to 100, 200 and 100 image where we can use we can reduce the number of parameters with when we reduce the image, the importance of reducing the images, we want to capture the real feature, right? So how do we, when we are getting the edges and textures, all those things, why do we want to reduce the image size again?
I didn't get the question.
So we have this
400 cross 400 image.
Yeah.
Okay.
And then in this 400 cross 400 image, we detect edges, textures, and gradient and all of those.
Edges, textures, gradient,
and we reduce this image to 200. Let's say
we reduce this image to 200.
Yeah.
We reduce this image to 200.
200 to convolution or to and in this 200 image, whatever features that we want, they will be glorified and all the background pixels will be off, right? So, and then when we have a 100, so this is the classical way of finding the object in an image. So, but when you're saying we want to connect all these images together, and thereby we want to reduce the number of parameters, I still do not follow how we are able to detect the images, and why do we need to reduce the images? If we are sure that all the images in the gradients are good in the 400 to 400 image, and we don't need to.
Okay, first of all, this is object size. This is not image size. So the object size is 200 cross 200 inside image of 400 cross 400, which is always the case. When you take photographs, you're not going to get consistently same size of objects. So my concern right now is that my object size is very small as compared to image size, and maybe very big also. Image size is still 400 cross 400. Now when I convolve on this guy, this object size, by the time I hit a receptive field of 200, the whole pixel is, one pixel represents the whole object now. And I need a way of directly connecting that, because if I convolve further on top, my 3 crossing is just going to destroy that part.
This is for the training part, or this is for
the model architecture part. We are discussing a model architecture. Once you've done this is done for life. Model is going to be like that only. Then we discuss that if this is true, which is what we are doing in YOLO, I can do something like this also. The moment I extract edges and gradients, if I pass on this to these edges and gradients, and I have a 1 cross 1 here also, or a skip connection like ResNet, it is going to wait till the convolution needs to happen to convert those edges into gradients, or to convert those edges and gradients into textures. Right? My edges and gradients are going to convert into texture. But let's say I am forced to go through 4 layers to do this, because the receptive field was large. But because now I have a skip connection or I have a 1 cross 1, I don't have to go through these convolutions. I can save my channel and finally compare.
Got it.
The connection is formed using one.
Connection is?
Formed using one.
Or skip connection, like in this one. Yes, so the bare minimum we need right now is the size of the image now. Assuming that our objects are going to be of that size. Now let's say we have a data set of cancer cell where the image size is big but the cancer cells are small. What is the receptive field I need now? That size, not the image size. That's the minimum I need now. It is the size of the object. That's the minimum I need now. That's why I'm saying cancer cells, which is always taken from microscope at a specific distance of a petri dish. So there the cancer cells are going to be exactly same in size, similar in size. Let's say these are RBC cells. So maximum cell is going to be still small as compared to the whole image. That's the least receptive field I need. But if I increase my receptive field, as we discussed, I'm going to capture many different orientations of these cells also. So it makes sense to increase them. Generally you are going to say 2x is a very good number. The moment you start going beyond 2x, you start seeing overfitting. You start seeing overfitting. Can I go to 3x? Yes, I can go to 3x, but I have to make my overfitting solve. I have to maybe look at a different image augmentation. Maybe I have to go for bigger image size also to make sure that data is actually linked back. 5x is possible. It is possible, but now even more difficult. This is where the difficulty is easy. At 2x, you can still train it. The moment you go at these numbers, you have to train it even harder.
So when we use that, we don't need to care about the image size, right?
Yes.
But in our spatial models, we usually by the input shape that the model will be expecting.
When you actually are using fully connected layer.
But if we don't give it a fully connected layer,
So you actually say null and null. This means that any size can come in.
so is it better to first reshape the image, resize the image into a proper one, or like random images, random sizes is okay?
Some datasets are fixed, 22 to 32. For ImageNet, dataset is 224 to 224 because the competition is at that. But object detection data size is not fixed. So YOLO trains on 224, 248, 268, 320. So it trains on many different resolutions. So it's not fixed there. But they definitely specify the input size as null, comma null. So any size can come in. No. Diagnostic tool, like thermometer. The layer which is very close to your final layer, and it has a good size also. Right now, one thing I did not cover here in the GradCamp part. Now let us again look at this particular equation. Here I am going to go inside my class ID. Right now the class ID is 180. I'm going to say 200. That is not the class which is there, but I'm going to run it for my network. What is going to happen now? Nothing. Nothing should happen. But let us say the class 200 was a sunglass, and let us say the dog was wearing a sunglass. You will find sunglass now. See, that ID is something you're starting with. That is not a permanent starting point. Your image has a dog and a cat. You saw the PDF also, right? We have image, we have our dog and cat both in the images. And if you run this through, let's say softmax is either going to say cat or a dog. Softmax is known for giving us one class. But when you see these GradCamp images, I can see both. You're getting grad camp for dog, you're getting grad camp for cat, both. That should not be possible if there's only one ID we can do derivative from or gradient from. So you define what you want. Let's say there's a bottle kept there. All you have to do is to go to ImageNet database, check what is the ID of the bottle class, and run the grad camp for that ID, and you will find that. That is one other assignment we gave in EVA also, where we gave a person wearing a goggle, and we asked them to find goggle using grad camp. All you have to do is to go on ImageNet dataset, see what is the ID of the goggle, and do grad camp for this particular ID, and you're going to get highlight exactly on top of the goggle.
How do we do for two different items?
We don't do for two different, we can do it for one and then followed by second one.
And then superimpose both?
You can if you want, but as you can see, we are not superimposing here.
So for for green and yellow side, so that was superimposition, the video that you were showing?
That is superimposition. So there you're adding some more logic there. You saw the paper, right? I was scrolling through, it said LSTM and RNN, so they're taking that part also. So you can make it even more complicated, but we are keeping our grad camp simple.
Still not clear if original data set has image with dog and cat code, but it is labeled with cat.
No, cat and dog both.
Or it will be labeled with both.
Yes. Generally, okay, this is not an image from ImageNet. ImageNet has one class per most of the images have one class per image.
But you
Single object. ImageNet is single object. ImageNet is single object. Single object per image. But you have 1,000 classes there. That many images, we can't see them, but some of the right, some of the classes which are there in ImageNet, and these are one object. They've tried to make sure that there's only one object per class. School, you understand the assignment? Please make sure you do assignment on time. I'm going to make sure that you get the images on time and you have enough time to finish those also. And try to be as racist, as biased as possible in your prediction. The aim is to capture that.